Okay, so in this section we're going to be exploring what's known as trigonometric substitution. And the three things we're going to need to know for this section, kind of like you can think of them as identities, trig integrals, are going to be these three things right here. And so this first thing, actually, this integral of secant theta, we're going to prove it. It's kind of going to be like our introduction to Trig Sub. How we're going to substitute things that seem really weird and seem like they actually make the integral more complicated at first. But then we're going to figure out some identities and some substitutions that generally make it seem a lot easier. So, for example, if I want to take the integral of secant theta d theta, what I'm going to do is I'm going to multiply it by 1. Because multiplying by 1 doesn't change our value. The thing is that when I multiply by 1, I'm going to write the number 1 in a really weird way. What I'm going to do is I'm going to write it as secant theta plus tan theta divided by secant theta plus tan theta. Right, so I have the same, the numerator and the denominator are the same, which means that this fraction that I've just created is equal to 1. And we don't have to worry about it being undefined or anything like that, because we assume that whatever domain we're working over here, secant of theta is going to be defined and continuous on that domain. Defined on that domain. And then, so when we work here, what I'm doing is I'm multiplying by secant theta plus tan theta over secant theta plus tan theta. So I just need to make sure that, all of these guys are defined. So what I want to look at is secant theta is 1 over cosine theta. Well, that has to be defined because this is defined. And tan theta is sine theta over cosine theta. And so the only thing that would give me an issue there is if cosine was 0. But it can't be because we already said that this was going to be defined. So what I've just multiplied by here is going to be okay. Okay, now let's look at how this is going to work out. So what I'm going to do is multiply out that secant theta to our numerator. And so we'll get secant squared theta plus secant theta tan theta over secant theta plus tan theta d theta. Okay, and now what I'm going to do, it kind of looks like I've made this more difficult than what we started out with. But here's the beauty of Trig Sub is that if we use the correct identities and the correct substitution, then this should get easier. And so what I'm going to do is I'm going to u substitute, and I'm going to use u equals our denominator. So I'm going to use u equals secant theta plus tan theta. Which means that we'll have du d theta is equal to the derivative of this right hand side. So that'd be secant theta tan theta plus secant squared theta. And then when I divide it over, we'll have secant theta tan theta plus secant squared theta underneath our du. And then this will be equal to d theta. And so now I can substitute that back into our integral. And we'll get the integral of secant squared theta plus secant theta tan theta divided by u times, then d theta is going to be equal to du over secant theta tan theta plus secant squared theta. And so now we should notice that this denominator and this numerator are going to cancel out with each other. And so what we'll be left with is just the integral of 1 over u du. Which means that this is going to be equal to the natural log of the absolute value of u plus c. And so now I just plug our u back in, and we get the natural log of the absolute value of secant theta plus tan theta plus c. Okay, so that's going to be our proof for that integral. So you can memorize it, or this is the trick for how you figure out what it's equal to. Alright, now I want to look at what is the general idea of trig substitution. So what we're going to be looking at is we're going to be looking at various different integrals. And inside those integrals, we want to identify them as form 1, form 2, or form 3. Right, so I'll be looking at that integral, and I'll try to find a square root with something that looks like a constant squared plus or minus x squared, or x squared plus or minus a constant squared. And that constant, we refer to it as a. Then once we've figured out what form we have, we use whatever substitution we're told to use. So one of these guys. And often that comes with us using some sort of identity. And this identity is supposed to make our integral easier. Now, I've also reminded us of the domain, right? So this is for sine inverse. And then this right here, this is going to be for secant inverse. And this one right here is going to be for tan inverse. Okay, so we need to remember that the domain of these functions, we want them to be 1 to 1, so that we can have these inverses be defined. And so to do that, we restrict the domain of these functions. So let's look at this first example, the square root of 1 minus x squared. Well, this to me looks like a minus x squared, or a squared minus x squared. So what I'm going to do is I'm going to write that down. We have I think it's going to be form 1. So I've got square root a squared minus x squared, and I want this to be equal to square root 1 minus x squared. And so then this tells me that a is equal to 1. So my substitution should be x equals a sine theta. Well, a is 1, so we're just going to have x equals sine theta. Oops. Then taking a derivative of both sides, I would get dx is equal to cosine theta d theta. And so now I can replace all of these x's in our dx with stuff that has theta in it, which is our first step for trig sub. Okay, so this integral becomes the integral of 1 over, so x squared, that'll be sine theta squared. So let's see, we'll have sine squared theta times the square root of 1 minus x squared, so 1 minus sine squared theta, times, and then dx is equal to cosine theta d theta. Okay, so what I notice here is that this 1 minus sine squared theta, that's our identity for cosine squared theta. And when we take the square root of that, that'll give us the square root of cosine squared theta, which will just be cosine theta. So this is going to be cosine theta d theta over sine squared theta cosine theta. So now these can cancel out, and I'll be left with the integral of 1 over sine squared theta. Okay. So from here, what we're going to do is we're going to change this. So sine 1 over sine is the same thing as cosecant. And we have an integral rule from Cal 1 of the integral of cosecant squared theta, d theta. And that should be negative cotangent theta plus c. Now this is great. It looks like we've gotten an answer. However, our answer should be in terms of x, right? We started with something in terms of x, so we need to go back and put this in terms of x. The way we do that is we take whatever substitution we used. So we take this part right here. So I have x equals sine theta. And so now I want to get theta in terms of x. Well, that's why I talked about this domain stuff. Because now to get it back, I'm going to take sine inverse of both sides. So I'll have sine inverse of x is equal to theta. And remember that by SOHCAHTOA, right, sine is equal to opposite over hypotenuse. So this is telling me sine inverse of x is equal to theta, that when I take my right triangle, I mark down theta, that the opposite over hypotenuse should be equal to x, which is the same thing as x over 1. So I'll make my opposite x, my hypotenuse 1, which means by the Pythagorean theorem that this must be the square root of 1 minus x squared. Okay, well remember tangent is TOA, so that's O over A, opposite over adjacent. So then cotangent flips it, so that's going to be adjacent over opposite. So I should have negative, so let's say the adjacent would be square root 1 minus x squared over opposite, so over x plus c. And then that would give us our answer for this integral. Alright, so to quickly outline the steps for this, you figure out what form it is, figure out a, make your substitution, find dx. Now once you have all of that, then we substitute everything into our integral. From there, we try to simplify things as much as possible. So we use a trig identity right here. Then we get a cancellation here. And then once we're there, we have something that we can apply an integral rule to. That will give us an answer in terms of theta. And so we isolate theta in our x equals substitution, form a triangle that allows us to solve for whatever trig function we have over here. Okay. So let's look at example 2 to hopefully maybe get a better idea of how to use all the forms and what to do in different situations. So this to me looks like the square root of x squared plus a squared, or as it says in the table, a squared plus x squared. So if I have square root a squared plus x squared, and that's going to be equal to square root x squared plus 9, then that tells me that a is going to need to be equal to 3. Because if I plug in a equals 3 right here, then the left-hand side and right-hand side will look exactly the same. And so here we're told that we're supposed to use x equals a tan theta. So I'm going to be using x equals 3 tan theta, which tells me that dx is going to be equal to 3 secant squared theta. So now we'll make our substitution. So this should be the square root of x squared. So that'll be 3 squared, which is 9, tan squared theta, plus 9, divided by x to the 4th. So this will be 3 to the 4th, tan to the 4th of theta, times dx, which is 3 secant squared theta. Oh, and we're forgetting d theta here. Okay, so this 3 will multiply out up top, and we'll have a 3 over 3 to the 4th, which will give us 1 over 3 cubed. So I'm going to pull that out in front, 1 over 3 cubed. And then inside my square root, I'm going to factor out the 9. So this is going to be the square root of 9 times tan squared theta plus 1. And then we should have times secant squared theta over tangent to the 4th of theta, d theta. And so now this 9, if I take the square root of 9, that's going to be 3. And so I can pull that out in front of our integral. So we'll have 3 over 3 cubed, which is the same thing as 1 over 3 squared. And 3 squared is equal to 9. Times the integral of... So then we'll just be left with... Oh, I forgot a parenthesis there. Then we'll just be left with the square root of tan squared theta plus 1. And our identity for tan squared theta is that tan squared theta plus 1 is equal to secant squared theta. And then times secant squared theta divided by tangent to the 4th of theta. So this will give me 1/9 times the integral of. So the square root of secant squared theta would be secant theta. So we'll end up with secant cubed theta on top, divided by tangent to the 4th of theta, d theta. And so this will give us, so if I break these up into 2 different fractions and multiply them, secant cubed theta, that's 1 over cosine cubed theta. 1 over tangent to the 4th of theta, that would be the same thing as cotangent to the 4th of theta. So that's going to be cosine to the 4th of theta over sine to the 4th of theta, d theta, which gives me 1/9 times the integral of cosine theta over sine to the 4th of theta, d theta. And now here we'll have a u substitution. So we'll use u equals sine theta, which means that du over cosine theta is equal to d theta. Then plugging in this u substitution, we should have 1/9 times the integral of cosine theta over u to the 4th. And then d theta is going to be du over cosine theta. So this is 1/9 times the integral of u to the negative 4th du, which will give us 1/9 times u to the negative 3 over negative 3 plus c, which will give us negative 1 over 27 u cubed plus c. Plugging in for u, this will give us negative 1 over 27 sine cubed theta plus c. And so now we need to get rid of theta. So we'll go back, we'll use our original substitution for x, which is x equals 3 tan theta. So I'll divide on both sides by 3, giving me x over 3 is equal to tan theta. And then I'll take tan inverse of both sides. Okay, so setting up my triangle, I should get that opposite over adjacent is x over 3. So then my hypotenuse has to be the square root of x squared plus 3 squared, which is 9. Okay, so then plugging this in, sine is so that's OH. So it's going to be opposite over hypotenuse. And so this is negative 1 over 27 times, so another way to look at this is that we have 1 over sine cubed. So I can think of it as 1 over sine. We just flip this, so this is hypotenuse over opposite. So this is going to be times square root x squared plus 9 cubed over x cubed plus c. And then that will give us our answer for our integral. And once I have this, once I've gotten everything in terms of x, I really don't care to simplify after that. Now let's look at example 3. So example 3 is a little weird because it doesn't look like x squared minus a squared. It kind of looks like that, except for we have this constant attached to x. So if I wanted to guess, our form was supposed to look something like x squared minus the square root of x squared minus a squared. Okay. Well, if I want that to be equal to the square root of 9x squared minus 4, I definitely need a is equal to 2, right? That'll give us our minus 4. And then what I'm going to do is I'm going to redefine. So this little symbol right here means that I'm redefining x being equal to 3x. And here's why. If I take this x right here and I replace it with a 3x, then this 3x squared gives me the 9x squared that I have right there. Okay, so now let's use our formula. So our substitution here is that we're supposed to have x is equal to a secant theta. And so now I'm going to replace this x and this a with what we found over here. So then we're going to have 3x is equal to 2 secant theta. And so now my goal is to get x alone. So we'll have x is equal to 2/3 secant theta. And then take a derivative. So we'll have that dx is equal to 2/3 secant theta tan theta. Alright, so now let's plug all of that in. So this becomes the integral of 9 times x squared. So that should be, let's see, that's going to be 2/3 squared, which is 4 over 9, times secant squared theta, minus 4, over x, so that's going to be over 2/3 secant theta, times dx, so it's going to be times 2 secant theta tan theta over 3 d theta. Okay, so let's see what happens here. Well, when I go to simplify this, these 9s will cancel. So I'll be left with a 4 secant squared theta there. So I'm going to factor that 4. We'll have 4 times secant squared theta minus 1 over. So I'm also going to take, so let's see, I'm going to take this 3 and multiply it with this 2/3. So it'll cancel out our 3's. And the other thing I'm going to do is I'm going to multiply this 2 out in front of our integral. So let's see, we should have 2 secant theta down here. I pull the 2 out in front of here. This is times secant theta, tan theta, d theta. And now I notice that my 2's here are going to cancel. Okay. Oops. Alright. And then I also notice another thing that's going to cancel, which is going to be these secant thetas right here. So this will give us the integral. So I can also now, this 4, the square root of 4, that'll give us 2. So I can pull that out of our integral. So this is going to be 2 times the integral of the square root of secant squared theta minus 1 times tangent theta over, so remember these guys cancel, so this will just be over 1 and then d theta. And so this is going to be 2 times the integral secant squared theta minus 1. Our identity for that is that that is equal to tangent squared of theta. The square root of tangent squared of theta will give us tan theta. So we'll have tan theta times tan theta d theta. And then what I'm going to do is multiply these together and then use our identity for tangent squared of theta minus 1. Sorry, just tangent squared theta d theta. And so this should be equal to secant squared theta minus 1. This is 2 times the integral secant squared theta minus 1 d theta. Which will give us, so now we can break this into 2 parts. Right, the integral of secant squared theta, that should be tan theta. And the integral of negative 1, that'll be negative theta. And plus c. And so now our goal is to change this back into x's. So we use our x equals 2/3 secant theta. And actually what I'm going to do is I'm going to use this one right here. They're both the same. It's just that starting with this one will give me one less step. So we have 3x equals 2 secant theta, which means that 3x over 2 is equal to secant theta, which means that secant inverse of 3x over 2 is equal to theta. And so that'll give me a nice picture of, so secant, that's 1 over cosine. Cosine is adjacent over hypotenuse. So secant should be hypotenuse over adjacent. So hypotenuse over adjacent is going to be 3x over 2. So then this has to be the square root of 9x squared minus 4. So this will give us 2 times tangent of theta. So it's going to be opposite over adjacent. So we'll have square root 9x squared minus 4 over 2 minus theta, which we have here. So it's going to be minus secant inverse 3x over 2 plus c. Oops, let me use a different color. Okay. Now, number 4, we're going to have a similar scenario going on. We're just going to use a slightly different form. So here, I've got something that looks like square root a minus x squared, but there's a constant attached to that x squared. So if this is going to be equal to square root 1 minus 9x squared, then I know a equals 1, and I'm going to redefine x to be 3x. That way we'll get this 3x squared here, which will give us our 9x squared. So our substitution for this one is supposed to be x equals a sine theta. And so then plugging in for x and a, this will give us 3x equals sine theta, which means that x is equal to 1/3 sine theta. So then dx must be equal to 1/3 cosine theta, d theta. So then plugging everything into our integral, we should get x squared on top, so that's going to be 1/3 squared, so that's 1/9 sine squared theta over the square root of 1 minus 9 times x squared, so that's 9 times 1/9 sine squared theta d theta. Okay, and then from here, I'm going to pull this 1/9 that's up top, I'm going to pull it out of our integral. So I'll have sine squared theta on top. Then on bottom, I'll have the square root of 1 minus this 9 times 1/9 will cancel with each other. So I should have the square root of 1 minus sine squared theta d theta. That will give us 1/9 times the integral of sine squared theta over 1 minus sine squared, that's cosine squared. So we're going to have the square root of cosine squared, which is cosine theta d theta. Alright, now what I'm going to use is that missing something. Oh, that's what I'm missing. This right here, this d theta, we never plugged in our dx. I, for some reason, just wanted to write d theta and be done with it. That's not how math works. So this is going to be times 1/3 cosine theta d theta. So this 1/3 right here should have been pulled out to the front, so this would become 1/27. So then we'd have times cosine theta d theta. So this would be 1/27. And now this makes a lot more sense. Right, because now we can cancel these out. And we'll be left with 1/27 times the integral of sine squared theta d theta. And so from last section, we should know that we will break this down using the identity that, one second, sine squared theta is equal to 1/2 times 1 minus cosine 2 theta d theta. And so this gives us 1/54 times the integral of 1 minus cosine 2 theta d theta. And then integrating this, we should have 1 over 54 times the integral of 1 is theta, minus, so the integral of cosine 2 theta, that should give me 1/2 sine 2 theta, plus c. And so now my goal is to use that 3x equals sine theta to set up our triangle. So 3x equals sine theta, which means that sine inverse of 3x is equal to theta. So sine, that's going to be opposite over hypotenuse, so I should have 3x over 1. And then this should be the square root of 1 minus 9x squared. Okay. So then our integral is going to be equal to 1 over 54 times theta, which is sine inverse of 3x, minus, so we have this sine 2 theta. What I'm going to do is I'm going to, so we'll still have our 1/2, but I'm going to rewrite sine 2 theta using another one of our trig identities, which is that sine 2 theta is equal to 2 sine theta cosine theta plus c. So this is 1 over 54 times sine inverse 3x. Our 1/2 and 2 will cancel with each other. So I have minus sine theta, which is going to be 3x, times cosine theta, which will be the square root of 1 minus sine x squared. And then this will give us our answer. Okay, moving on to example 5. This is going to be a good chance for us to practice what happens when we end up with definite integrals inside of trig substitution. Okay, so we'll just want to be careful that when we're doing all our substitutions and everything, that we're changing limits as need be. So, first thing I notice is that I've got something that looks like square root x squared minus a squared. And this is supposed to be equal to square root x squared minus 25. So I'll get a equals 5. And since we don't have any constants attached to the x, I don't need to redefine our x value. So this tells me that we're supposed to use x equals a secant theta, so that'll be 5 secant theta, which means that dx is going to be equal to 5 secant theta tangent theta d theta. Now, we've made this substitution of x equals 5 secant theta. These limits up here are for our x values. So if I'm going to be changing things to be in terms of theta, then those need to be plugged in to our substitution equation. Right? And they need to be plugged in for x. So we should have 10 equals 5 secant theta. So that will give us 2 equals secant theta. So we'll have secant inverse of 2 equals theta. And so here's the thing, is it may not appear inherently obvious as to what secant inverse of 2 is. So I want to give you a different way to think about it. I want you to think of secant of what angle is going to give us 2. Right? Now, maybe a better way of thinking about that is that 1/2 is equal to cosine theta. And we need to remember that we're staying in the domain from 0 to pi. Right? So, well, and not including pi over 2, because we want secant theta to be defined. So, the angle that we should be looking at on our unit circle, the one that gives us 1/2, is going to be the one right here. And that's going to be at pi over 4. So that tells me that theta equals pi over 4. So that will replace our upper limit. So we're going to have the integral. So it becomes our upper limit. Then for our lower limit, we should have 5 root 2 is equal to 5 secant theta. So that tells me that square root 2 is going to be equal to secant theta, which means that 1 over square root 2 is equal to cosine theta, which means that square root 2 over 2, right, I'm multiplying by square root 2 on top and bottom of the left-hand side, is equal to cosine theta. And I just realized I made a mistake. When you look at the unit circle, 1/2 is the smaller of our x values, so this should be pi over 3. And then this will give us pi over 4 is equal to theta. So it should become pi over 4. Okay, now plugging everything in. So on top we have dx, so it's going to be 5 secant theta tan theta d theta over x cubed. So that should be 5 cubed secant theta times the square root of x squared. So that would be 25 secant, oh, that needs to be secant cubed theta. Secant squared theta minus 25. And so this becomes, okay, so I have 5 over 5 cubed. That'll become 1 over 5 squared. So I get 1 over 25. Whoa. Yikes. So I get 1 over 25 times the integral from pi over 3 to pi over 4 of secant theta tan theta d theta over secant cubed theta square root, I can factor out a 25, so this becomes 25 secant squared theta minus 1. Okay, so the square root of 25 is 5, so I can pull that out. So this becomes 1 over 125 times the integral. So I notice on bottom, or we have a secant over secant cubed. So that's 1 over secant squared. So I should have tangent theta d theta over secant squared theta times, so we've pulled that 25 out. Secant squared theta minus 1, that's tangent squared theta. So if we take the square root of that, we'll end up with just tan theta. Okay, so this will give me, for 1 second. So this will give me 1 over 125 times the integral of 1 over secant squared theta d theta. Okay, so from here, if we have 1 over secant, that's the same thing as cosine. So this should be 1 over 125 times the integral from, oh, let me keep these integration limits in here. Okay, so we should have cosine squared theta, d theta. And so now we need to remember how to integrate cosine squared theta. So we should be using our identity, which states that this becomes, so cosine squared theta is the same thing as 1/2 times 1 plus cosine 2 theta, d theta. And so this becomes 1 over 250 times the integral from pi over 4 to pi over 3 of 1 plus, so for cosine 2 theta, we have a formula for that. So that's going to be, actually we don't, in this case we're not going to need to because we have definite limits. So we're just going to go ahead and integrate this. So the integral of 1 will give us theta. The integral of cosine 2 theta will give us 1/2 sine 2 theta. And then plus c. Okay, and the thing that I'm missing, so this is a definite integral. So we're just going to take this and evaluate from pi over 3, from pi over 4 to pi over 3. Okay, so let's see how this works out. This will give me 1 over 250 times, so I plug in pi over 3, I'll get pi over 3 plus 1/2 sine of 2 theta, so that's going to be 2 pi over 3, minus pi over 4 plus 1/2 sine of 2 pi over 4, which is pi over 2. So then this becomes pi over 3 minus pi over 4. That would be the same thing as 4 pi over 12 minus 3 pi over 12. So that's going to give us pi over 12. Plus sine of 2 pi over 3. So if we're looking at our unit circle, 2 pi over 3 would be this point right here. And so that means that sine of 2 pi over 3 is going to be square root 3 over 2. So that should give me 1/2 times square root 3 over 2 minus, so let's see, we already took care of our pi over 4, so then I should have minus 1/2 sine of pi over 2, so it'll just be minus 1/2. And so this will give us our final answer. Now moving on to example 6, we'll get another chance to practice these definite integrals. And the first thing I'm going to do is change this to look like something that has a square root. So this to the 5/2 power, that means I'm taking the square root of 4 plus 9x squared to the 5th. Okay, and so what I'm going to be looking at is that our form is looking like square root a squared plus x squared, right? Except for we have to the 5th power. If I wanted to, another thing I could do is just make this the square root of 4 plus 9x squared, and then raise it to the 5th outside like this. So we'll just plug it in inside those parentheses. So we still have this form that we need. So So we've got the square root of a squared plus x squared. And we'll need to redefine x. So we'll have x is redefined to be 3x. And a will be equal to 2. And then our substitution we should be using is that x is equal to a tan theta. So we'll have 3x equals 2 tan theta. And then isolating x, we'll get x equals 2/3 tan theta. And so taking a derivative on both sides, I'll get dx is equal to 2/3 secant squared theta d theta. Okay. So from here, what I'm going to do is go ahead and figure out our limits. So I should have 2/3. If I plug that in for x, I should have 2/3 is equal to, and I'm using this equation right here. 2/3 is equal to 2/3 tan theta. So this means that 1 is equal to tan theta. So theta must be equal to pi over 4. Okay, then I'll have 0 is equal to 2/3 tan theta, which tells me that 0 is equal to tan theta. So theta must be equal to 0. So then our integral becomes the integral from 0 to pi over 4 of dx, which was 2/3 secant squared theta d theta, divided by, now I should have the square root of 4 plus 9 times x squared. So x was 2/3 tan theta, so this is going to be 4 over 9 tan squared theta. Okay, so I can pull this 2/3 out to the front. I'll have secant squared theta on top, secant squared theta d theta. Oh, and this should have been raised to the 5th power. Okay, and then I should have, let's see, this is going to be 4 plus 4 tan squared theta, because our 9s will cancel down here. So this is 4 tan squared theta, and what I'm going to do is go ahead and pull that 4 out. So this is going to be, actually, give me 1 second. I'm going to be really careful when I do that. So the thing that I'm being really careful about is this exponent to the 5th. So this should be secant squared theta d theta. Then I'll have the square root, so I can factor the 4, so that gives me 4 times 1 plus tan squared theta to the 5th. And so then this becomes down on the bottom, the square root of 4 is going to be 2. But it's still going to be inside these parentheses, which means that 2 is still getting raised to the 5th power. So that's why we get 2 over 3 times 2 to the 5th, which is 1 over 3 times 2 to the 4th times the integral from 0 to pi over 4 of, let's see, well, secant squared theta d theta over, let's see, this should be, I'm going to go ahead and rewrite this as a fraction now, so we'll have 1 plus tan squared theta to the 5/2. So then this becomes 1 over 3 times 2 to the 4th the integral from 0 to pi over 4 of secant squared theta. 1 plus tangent squared theta is secant squared theta. If I take a square root of that, that'll give me secant theta, so then this becomes secant to the 5th theta on bottom. Alright, now that I'm there, we'll proceed to move on by trying to actually integrate this. So I should have 1 over 3 times 2 to the 4th is equal to, times the integral from 0 to pi over 4 of 1 over, and I need to remember my d theta, 1 over secant cubed theta, d theta. Okay, so this would be the same thing as 1 over secant is the same thing as cosine, so this is cosine cubed theta. And so now we'll need to integrate this. Well, by the previous section, our rule when we have an odd exponent for cosine is that we should factor out a cosine. So let's see. We'll factor out a cosine, so this becomes cosine times cosine squared theta. And then we rewrite this using that cosine squared theta is equal to 1 minus sine squared. So this is 1 minus sine squared theta, d theta. And so we get 1 over 3 times 2 to the 4th, the integral from 0 to pi over 4 of, what I'm going to do here is I'm going to go ahead and use u substitution. So I'll use u equals sine theta, and then we'll get du over cosine theta is equal to d theta. So our integral becomes, oh, I'm missing cosine, the actual theta part of this. So this becomes cosine theta times 1 minus u squared times du over cosine theta. And so we get, let's see, we'll have 1 over 3 times 2 to the 4th. Now, the one thing I've forgotten to do is that we need to change our limits here, right? We just used a u substitution, so we need to change the limits. So on top, I'm plugging in pi over 4 to sine of theta. So that'll give me square root 2 over 2. And on the bottom, I'm plugging in 0 to sine theta, so that'll still give me 0. Okay. So then this will give us, our cosine thetas can cancel. So we're just left with 1 minus u squared du, integrating from 0 to square root 2 over 2. Okay, and then when I integrate this, we should get u minus u cubed over 3, evaluating from 0 to square root 2 over 2. And so this becomes 1 over 3 times 2 to the 4th of square root 2 over 2 minus, so let's see, this is going to be square root 2 over 2 cubed. So that would be 2 root 2 over 8 over 3. 2 to the 4th, that should give us 16, so this is 1 over 48 times square root 2 over 2 minus, let's see, 2 root 2 over 8, that's root 2 over 4, so this is root 2 over 12. Okay, and then we could simplify from there if we need to, but there's really no need to. So it's fine for us to just leave our answer like this. Honestly, it would have been fine for us to leave it right here as well. Either one of these would have been good. Okay. Now we'll proceed to example 7, which is going to be our second to last example. And in these last two examples, we're going to work with completing the square. So here, I don't have anything that looks like square root x squared minus a squared. So what I'm going to do is notice that x squared minus 8x is equal to, so what I'm going to do here is I divide negative 8 by 2. So that'll give me x minus 4 squared. Now if I FOIL that out, that's x squared plus 16 minus 8x. So I have to get rid of that extra 16 that I've added. So this is minus 16. Okay. And so now our integral would look like 1 over the square root of x minus 4 squared minus 16 dx. And so now I have something that looks like x squared minus a squared. So we'll have to redefine x to be x minus 4. And we'll have a is equal to 4. So here I should be using x equals a secant theta. Which will give me x minus 4 is equal to 4 secant theta. And so I'll add the 4 over. That tells me that x is equal to 4 secant theta plus 4. So then dx is equal to 4 secant theta tan theta d theta. Now plugging everything in, I should get the integral of 1 over, so let's see, we'll have the square root, get rid of that. Let's see, x minus 4 squared. So that's going to be 4 secant theta plus 4 minus 4 squared minus 16. And then dx should be 4 secant theta tangent theta d theta. So I'm going to pull that 4 out. So I have 4 times the integral. On top, we should have secant theta tangent theta. On bottom, so let's see, these will cancel, giving me 16 secant squared theta minus 16 d theta. So what I'm going to do is factor out that 16, which will give me a square root of 16. So I'll get a 4 outside here. And then we'll have 4 times 1/4, which will give us 1. So we get the integral of secant theta tangent theta over square root secant squared theta minus 1. Right, that came from factoring the 16 out. You take the square root of it, so you get a 4 here. And then we pull out that constant 1/4 and multiply it with this 4, which gives us 1 in front. Okay, so then this will give us the identity for secant squared theta minus 1 is tangent squared theta. The square root of tangent squared theta will give us tan theta. So we'll get secant theta tan theta over tan theta d theta, giving us the integral of secant theta d theta. And so now we'll use what we proved at the beginning of this, which is that this is equal to the natural log of the absolute value of secant theta plus tan theta plus c. So now I need to use what we started with, which was x minus 4 equals 4 secant theta. So let's see, we have x minus 4 equals 4 secant theta, which means that x minus 4 over 4 is equal to secant theta. That'll be good because this will work for plugging in for that. But I'm going to go ahead and take a secant inverse real quick so that we can set up our triangle. So this is secant inverse x minus 4 over 4 equals theta. Alright, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant flips it. Secant gives us hypotenuse over adjacent. So we should get x minus 4, 4, and then this would have to be the square root of x minus 4 squared minus 4 squared, which will give us x squared plus 16 minus 8x minus 16. So this just becomes x squared minus 8x. And so this will give us the natural log of the absolute value of secant theta, which we already know is equal to x minus 4 over 4. This is x minus 4 over 4, plus we had tangent theta, so it should be opposite over adjacent. Right, remember we're using theta there. So opposite over adjacent will give me square root x squared minus 8x over 4, and then plus c. So that's one of the ways that we can complete the square in our trig sub integrals. The other way is going to be seen on example 8 here. And what I'm going to do is I'm going to try to change this into something that looks like x plus b squared plus c. So first, I'm going to take this linear term and divide it by 2. So it'll give me 3x. And so I'm just paying attention to the coefficient. So I'm going to use, let's see, well, x squared plus 6x plus 13. I want that to be equal to x plus 3 squared. That would give me a plus 9. So in order to get plus 13, I need to add 4 more to it. So this integral is equal to 1 over the square root of x plus 3 squared plus 4. Then we got to cube this. And so I have something that looks like x squared plus a squared. Right. So the form we should be looking at is square root x squared plus a squared, where we have to redefine x to be x plus 3, and we'll have a is equal to 2. Okay, so in this case, we should be using x equals a tan theta. All right, so let's write that down. X equals a tan theta. So that means that x plus 3 is equal to 2 tan theta, which means that x equals 2 tan theta minus 3. Taking a derivative on both sides, we should get dx is equal to 2 secant squared theta d theta. So this integral will become, if I put dx on top, then this is 2 secant squared theta d theta over the square root of, so let's see, we'll have x plus 3 squared. So that's going to be 2 tan theta minus 3 plus 3 squared plus 4. And then we need to cube this. Okay, so I'm going to pull this 2 out front. We'll still be left with secant squared theta d theta on top. Over, let's see, we should have, these 3's will cancel. So I'll have the square root of 2 tan theta squared, which will give me 4 tan squared theta plus 4. Now I can factor that 4 out to here, out in front, and we'll have a square root of 4, which will give me the 2 still inside the parentheses. So we'll have a 1 over 2 cubed we need to pull out. So it'll give us 2 over 2 cubed, which is 1 over 2 squared, so 1/4, times the integral. And so what we just did there is we got rid of this 4 inside of our square root. So we'll have tan squared theta plus 1, giving us 1/4 times, let's see, we should have secant squared theta d theta. Tangent squared theta plus 1, that's our identity for secant squared theta. So we'll take a square root of it and get secant theta. So I should have secant cubed theta on the bottom, which gives me 1/4 times the integral of 1 over secant theta. So just the integral of cosine theta d theta. And then I think this here is probably the nicest integral we do all day, because this will give us 1/4. I don't know what kind of 1 that was, but this is 1/4 sine theta plus c. And so now I'll use our x plus 3 equals 2 tan theta so that we can set up our triangle and solve this last tricky problem. So we should have x plus 3 is equal to 2 tan theta, which will give us x plus 3 over 2 is equal to tan theta. So tan inverse of x plus 3 over 2 is equal to theta, which means that our triangle should look like, let's see, opposite over adjacent, so this is x plus 3, this is 2, so it'll be the square root of x plus 3 squared plus 2 squared, which will give us x squared plus 6x plus 13. Okay, so then this is 1/4 times sine of theta. So that's going to be opposite over hypotenuse. So this is times x plus 3 over the square root of x squared plus 6x plus 13 plus c. And then that will finish our lecture for Trig Sub. And don't forget that this will be on the quiz due on Sunday.